in the School of Information and Library Science at UNC Chapel Hill. He also leads the Visual Analysis and Communications Lab, where he conducts research related to the study and development of visual methods for information analysis and communication, and serves as the Assistant Director for the Carolina Health Informatics Program. Before coming to UNC, he was a research scientist at the T.J. Watson Research Center at IBM Research. And finally, David is one of our NCDS Data Fellows, and this talk will address his Data Fellows research project. In case you don't know, the Data Fellows program is open to faculty members at NCDS member institutions, and each fellow receives a year of support for work that addresses data science issues, research questions in novel ways, and especially ones that are of interest to our members. Today's talk will last about 30 to 40 minutes with time for Q&A at the end. Please feel free to type your questions into the chat box as we go along, but we'd really like to hold the questions until the end of the presentation, and then we'll get back to them at the end. So thank you again for coming, and welcome, David, and I'm going to turn it over to you now.
Great. Thank you very much for that introduction. So once again, my name is David Gotz from UNC Chapel Hill, and I am going to talk about the work that my colleagues and I have done looking at ways to visualize high-dimensional temporal event data. My group focuses more broadly on all sorts of different things and ways to basically apply analytics and interactive visualization to help people make sense out of data and to communicate their insights. But again, today I'm going to focus primarily on temporal event data, which is a really important kind of data that is pretty broadly available in lots of different domains. So at its basic definition, temporal event data is just really a sequence of things that happen over time. So you can think of a recent business trip I had, for example, being modeled as a series of airport visits where I'm arriving and departing at different places. So here I had a trip that started in Raleigh-Durham, went to Atlanta, departed Atlanta, arrived in Paris, left Paris, arrived in New York, left New York, arrived in D.C., and then finally made my way back to Raleigh. So that's a pretty complicated itinerary, and so we can associate with that trip perhaps an unhappy face, so I have a negative outcome as a result of that kind of trip. Meanwhile, someone else might have a different trip that results in a better outcome. Much simpler non-stop flight. And what we can do is then collect this event data tied to outcomes for lots of people and start to reason about it to try and derive insights. So in this case, we might find that there's a period of time where a group of people were in Paris together. Maybe if we looked at thousands of people instead of just two, we might find that on average, most people actually have a better outcome for their business trip if they end up in Paris than somewhere else. Or we might be able to learn, for example, that longer event sequences where we have lots of different types of stops lead to worse outcomes. So that's the kind of stuff that we want to be able to do. Collect records of people or machines or events in different ways, and then get large collections of these things and try and derive some insights. So as I mentioned, this kind of data is available in lots of different domains. I have a colleague that I've worked with and a student when he was a student mentor. He is now on the data science team at Twitter, and they collect a lot of data about the temporal sequence of events that you perform using their service. All the different posts you make, the retweets, things you like, or the contacts you make. The same thing with Facebook. You have your posts and shares and likes and friends and unfriends. You also have events like clicking on things and scroll bars and hovers over different types of visual elements in the page. All of those things are collected and analyzed to try and figure out how best to drive traffic and increase revenues and all sorts of other business metrics. Similarly, in computer security, we capture security logs for all of our devices. We capture network connections that come in, network connections that go out, secure system logins of different kinds, failures and exceptions, policy overrides, all sorts of events that happen over time that we can then try and analyze in bulk to try and understand how those patterns and the different ways that those events unfold lead to differences in some measurable outcome of interest. The domain that I focus on for a lot of my work, because it contains all of the kinds of problems that I'm going to talk about, and also it has some really important driving questions that we want to answer from data, is healthcare. So if you think about your electronic medical record, these days when you go into the doctor's office, stuff is entered into that electronic medical record and saved away. You come back the next time and more things are entered. Often that's kind of thought of as almost read-only. Your doctor will review a little bit of it when you come in. But if you think about how that's working for the entire population of patients who are going through a large medical provider, you have tons and tons of event sequences. You have office visits, you have hospitalizations, you have diagnoses, medications, procedures, different kinds of lab tests that happen. There's all kinds of categorical data, demographics, social information. Now we're getting DNA, genomic information that's getting pulled in for precision medicine. So the number of different things we know about patients is growing quite large. And a lot of it, perhaps the bulk of it, is actually spread out over time as these time-sampled events that unfold as you get sick and get better. A couple of specific examples where I kind of motivate a lot of my work here at UNC. We have data, for example, in the UNC Healthcare Clinical Data Warehouse, where they have a warehouse that collects data from across the UNC healthcare system, which is roughly a dozen hospitals, many outpatient facilities with more than 3,000 physicians. Millions of patient records are collected into this repository, and all sorts of information is being pulled into it. Now that's captured mostly for operational use and delivering care, but this clinical data warehouse with the right privacy constraints and IRB approval can make that data available for research. And so researchers are looking at ways to make the healthcare system more efficient, to improve outcomes, and all sorts of other interesting scientific questions. A second resource here at UNC is housed by the Lineberger Cancer Center, where they have an integrated cancer surveillance system, which captures mandatory reporting on all cancer cases throughout the state and brings in a bunch of other information to contextualize that, for example, data about healthy patients, in order to support outcomes research, to figure out where interventions might be most effective in terms of getting people in for screening, all sorts of different kinds of questions. And that's being done by looking at millions of patient records from across the state of North Carolina, again with the right security and IRB approval that's being put in place to protect that information. But once we have those collections of massive numbers of patient records, what we'd really like to be able to do, if we're kind of dreaming of what the ideal view should be, in my mind, is we want something that's kind of GPS-like for our analytics, where based on this data, which captures how patients evolve, or Twitter users evolve, or computer hackers evolve over time, we can capture where the different roads are, who's following what different path, what outcomes those paths lead to, and when we might want to follow the main path, perhaps that's the best thing overall for most people, or deviate into the road less traveled, this side road that you see in the picture here, that might get the best outcome for this particular subpopulation because they're different in some way than the overall population. So with that vision, right, there are a lot of opportunities in analyzing this kind of large-scale temporal data. We have lots of population data that's captured in the real world that tells us about common patterns and overall trends if we can figure out how to look at it the right way. We can also start to identify specific events or subsequences of events or perhaps narrow focused subpopulations that in interesting ways are associated with better or worse outcomes so that we can either try and replicate that in some way or to intervene to prevent that from happening. Again, this is across different domains. But in order to reach those opportunities, we have to overcome a few different significant challenges. So these challenges might seem familiar for anyone who's worked with kind of big data type things in the past. One of them is scale, and that is we have not just thousands or tens of thousands, but often millions of these kinds of sequences, if you think about those electronic patient repositories. In addition to those millions of patients, we also have often long event sequences. It can be thousands of individual events for each sequence, so if we have millions of patients and thousands of events, we're getting into pretty big numbers. But really, the scale is not the major challenge that we have to overcome. If you think about visualization, if the data is simple, visualization works pretty well to summarize. If you have 10 billion patients and you want to summarize the gender distribution between male and female, well, a bar chart will work pretty well, just as well as it will for 100 patients or 10 patients. So this ability to scale by kind of counting and looking at some statistics is one of the powerful things about visualization that makes it really effective to use in looking at complex data. Now, there are computational challenges that have to be overcome, but in many ways that's where most of the focus has been in terms of large-scale data science, or at least most of the progress. If you think about things like Hadoop and all the derivatives, there's a lot of technology now in place that makes it much easier to scale up your computational analyses, especially if you can parallelize them and distribute them out across an infrastructure. So the scale really isn't the biggest challenge, but I think it's a bigger challenge, especially for visualization, but really for all data science, and you could think machine learning, it's also plagued by this, is the complexity and the variation within the data itself in terms of the number of different kinds of things we know, or the different dimensions. So in a data set like the medical case, we have lots of different kinds of events. They're sparse and irregular over time. You might see a doctor every 6 months and then skip for a couple of years. Meanwhile, someone else is going to see the doctor every week because they have something really serious. And those kinds of variations make it much harder to simply aggregate and summarize what you're looking at. So to drive that problem home just a little bit more, let's just look at some real numbers from the medical case. So if we are thinking about a database of electronic medical records where we're capturing information about patients over time, one of the things we have in there is diagnosis information. So diagnoses are typically coded with a coding scheme. So a common one you may have heard in the news that we're moving to is called ICD. We're moving to ICD-10, currently in place is ICD-9. ICD-10 has about 68,000 unique diagnosis codes. Version 9 has a few less, but still we're talking tens of thousands of different diagnosis codes. If we add in procedures, it's another 9,000 unique procedure codes for different things that can be done to a patient. We have countless lab tests, medications, and more. So we're already talking about tens of thousands of dimensions, millions of event sequences, billions of individual events if we start multiplying them out by this length, each of which is leading to different outcomes, all of which is thrown into this big, at least logically speaking, a big database. So what the research question I'm trying to focus in on my work is, what methods can we develop that can support more effective visual analysis of this kind of information to help people get more accurate insights, but also be more efficient and to do this kind of work much more quickly than they would if they had to perhaps go back into SAS and write a bunch of code to try and analyze their data and query against a database with structured query languages. So for the rest of the talk, I'm going to spend time kind of reviewing my journey, if you will, along this path and some of the different types of visualization designs and methods that I've developed, and kind of highlight what I'm working on currently before I wrap up. So with that, let me go on to kind of the place I started, which is work that began when I was at IBM Research. As you heard in the introduction, I was there until about 1.5 years ago when I moved to UNC about January of last year. And so the first thing that I'd like to talk about is this visualization called Outflow, which takes a relatively simple approach to try and solve this problem, which is that let's just select a subset of relevant dimensions that we want to deal with first. Let's try and aggregate them like we do in traditional visualization, like the bar chart example I talked about, and then come up with a way of depicting these different pathways and the outcomes that are associated with it. And so there are those 3 level steps. We need to select the relevant dimensions, aggregate our data into this kind of flow-based representation, the different paths that people flow through over time. And I say people here because I often think in terms of the medical use cases, but this will work equally well if you're looking at device logs of some kind, and so they're devices instead of people. But what we're trying to do is capture all the variation between those different event sequences, plot them, and try and render them visually. So the first step here, which I mentioned, is this notion of selection, the relevant dimensions. And so in Outflow, and in a lot of the work of its era, and I'll give some other examples, that's really what we kind of started to do, is that let's just pick dimensions from this thousands of dimension space. Let's pick a handful that we think are most relevant to the question that we're trying to answer, and use that to structure our visualization. So after that selection process happens, we then kind of build this data structure that you see here, which is basically a directed graph where things go from left to right. Where we start all the way on the left, we don't have any events at all. The first event that happens is kind of the next column, which is, in this simple example, we have 3 possibilities. Either event A happens first, or B, or C. After event A, we might see A and B both happen. Right? So you can have A first, then B. You can get to the same place by having B first, then A. And we can capture all these different permutations, and we get this kind of graph. If we attach the number of event sequences that travel along each of these paths to the edge or the node that corresponds to where they are, we can calculate some statistics. So things like average outcome, the amount of time between events, and the number of items that follow that path. So the number of patients, for example. Once we have that data structure, we can then encode that visually in the way you see here, where each of those nodes in that graph turns into a rectangle, where it again flows from left to right. The size of the rectangle in terms of its height represents the number of people or the number of event sequences that go through a path. We can then add additional edges here to represent the duration it takes to travel from one point in that node to the next, so the average duration, and we can add these link edges. And then finally, we can color them based on outcome, so we can see differences in people who traveled one path versus another. So this is a simple example. Let me kind of pivot to a video here that shows a real-world example where we're now applying this technique to a set of patients who are similar to a heart failure patient that we're trying to analyze. And here you can see the user starting to interact with the visualization. And I'm going to back up to one spot right here where the user has moused over a set of edges. And this corresponds to the kind of thickest path through the visualization. That means it's the one that happens most frequently within the data set. That, in practice, turns out to be the clinical guideline for treating heart failure patients. So in this case, we're looking at medications and the order in which they were prescribed and trying to see whether there are any differences in outcome. And that thickest path corresponds to people getting medications, if you will, in order, from step 1 meds to step 2 meds, step 3 meds, step 4 meds. But it turns out for patients who are most similar to this person, a more aggressive treatment, which you see in this path right here, actually produces better outcomes than the guideline-based treatment, because we're looking now at patients similar to this person who has a bunch of other confounding factors, right? We're not just looking at medications when we're trying to do similar patients. We're looking at a whole bunch of other features in this high-dimensional feature space. So this tool allows you then to do a bunch of other kinds of exploratory analyses directly through the UI. And you can do things like redefine patient outcomes, for example. What do we mean by an outcome? We started with hospitalization or death within 12 months. We can change that to only focus at death, and to apply filters to look at only pathways that led to a patient dying, and start to see whether we see any commonalities. And we can do pretty flexible analysis, right? But again, we're only limited to a relatively small number of events that we selected, in this case, the specific medications. So one thing we tried to add to this particular view is this side panel that you see on the right. So once a user selects one path through this visualization, what they've essentially done is selected a subgroup of patients who receive this specific treatment regimen, and that's a different treatment regimen than all the other patients who are in the similar patient set. But we're only looking at differences in the pathways based on the small number of events that we pre-selected. So what we can also do is analyze over all the other things that we have in the medical record and try and look for things that are unusually rare or unusually frequent for that subgroup. And we can show those on the right here to try and contextualize why that patient is moving down that particular path. It's not just that the doctor randomly chose to give this medication. There are perhaps other things that might be driving that. So that helps with a deeper understanding. And that helps us a little bit dig deeper beyond this small number of dimensions, but we're still pretty limited. So what are we going to do to scale to higher dimensions? Well, as I mentioned, pre-selection is really the way people started attacking this problem. So in the heart failure example that you see here, we pre-selected 18 event types. And already you can see it's pretty complicated. There's a lot of variation because we're capturing all the permutations that we see within those 18 symptoms in this case. for heart failure patients. And the symptoms appear in lots of different orders, so we have lots of different paths, and it gets really complicated. And so we have lots of visualization kind of rendering algorithms to try and simplify that, but there's only so much we could do. Similarly, this other work from the University of Maryland on life flow only had 6 event types. They color-coded their event types. So you can see if they're color-coding things where we can't scale beyond more than a handful, they're going to be dealing with a very small number of event types. So in order to try and overcome that and get to higher dimensional space, people have looked at things like simplification. So we had that in our own technique where we would collapse similar nodes. Monroe et al. Have a system where they tried to draw everything in its full complexity and then look for repeated patterns and kind of substitute. Instead of that big pattern, let's look at this just one event. And we've done some pattern mining work in my own team that has tried to come up with that sort of approach, where we can start with the most complicated view and then simplify down. But the most complicated view is really complicated, and it makes it really hard to see anything, which is the whole point of visualization. So in more recent work, we kind of took a new view at what we're going to do with this kind of data. And we designed a new system and new visualization techniques specifically focused to scale to these tens of thousands of event types in cases where you couldn't pre-select the 18 events that you wanted to deal with right away. And instead, you needed to kind of start from the beginning and surface the ones that might be most interesting over time. So that's kind of the model we wanted to take. Start simple, and then provide the tools that will let a user select the events from this big pool of possible events, select which ones are most important, and drop them into the visualization to add the complexity incrementally. So start simple and add complexity, rather than start complex and simplify. So we attack this by kind of looking at our data in a slightly different way, where instead of just a simple event sequence, we now introduced a 2-tier representation where we had a notion of milestone events. These are kind of more important events between which we had a bunch of intermediate events. Those are the less important events. But over time, we want to be able to surface those intermediate events, make them milestones, or perhaps turn a milestone into an intermediate event, and allow events to transition between these 2 different types. So given this definition, we then added kind of 2 invariants to our representation for lots of different event type sequences. Remember, we're capturing this for thousands or tens of thousands or millions of different patients. And so we have a couple of invariants for this. First is that all of our event sequences have to start with the same milestones. So you can think of those milestones almost as your query. So in this case, we're looking for patients who have angina followed by heart failure. And we also said that patients have to start and end with the same milestone. So we can look for a year's worth of data before angina and kind of bound both patients here in this example of 2 patients with this kind of implicit milestone that's the start of the time window 1 year before angina and ending with heart failure. Now, once we have this kind of structure, we can then split all of our patients. If we're dealing with medical data or if we're dealing with device data and security logs, we can split our security logs into subsequences at each milestone, and then we can group those together and then merge them into kind of a composite representation where we have this high-level set of milestones, and then we can anchor all those individual sub-event sequences to the edges in this representation. All right, so with that representation, the next thing we want to do is think about how we're going to allow people to choose among the intermediate events that happen between, say, angina and heart failure, which ones are the ones that are most relevant to our analysis so that we can surface it and promote it into a new milestone. And so to do that, we calculate a bunch of statistics for those subsequences that are anchored at each edge. And these can be relatively simple, right? Things like event type frequency. So how many patients in that time period had ankle edema? We also look at the association between good and bad outcomes. So what fraction of good outcome patients had ankle edema, what fraction of poor outcome patients had ankle edema, and then from that we can also look at correlation, odds ratios, even p-values to see whether we think the variation that we see is likely to be occur by chance or unlikely to occur by chance. And these statistics, again, are all designed to help people look through this pile of intermediate events that happen between the milestones across perhaps tens of thousands or hundreds of thousands of patients and figure out which events are interesting for the particular outcome question that we're studying. So once we find an event that we think is statistically interesting, so for example, the ankle edema event that I was mentioning before, let's say that's represented by the green diamond here. The first thing we do is we look for that green diamond, that ankle edema event, in all of those subsequences that are anchored to that edge. And then we can do similar to what we did before. We can split those subsequences, the ones that have ankle edema, into two pieces, before this green diamond and after the green diamond. That's before ankle edema was diagnosed and after. And then we have another group of patients for whom they never had ankle edema, right? The people for whom they don't have this newly promoted milestone. And so we can turn this one edge that we had into three edges, where we have a group of patients who had ankle edema. That forms two edges, the before events and the after events, and then the people who don't have that new milestone that we're promoting. And once we create these new edges, we can recalculate all those statistics that I mentioned before, and we can recursively do this process where we're kind of constantly promoting a new event because it's statistically interesting and adding it to our data structure. Now, that's promotion. We can also kind of take nodes away, and perhaps we added ankle edema, we thought it might be interesting, but once we looked at the data with the visualization, it's not interesting anymore. We can kind of remove that from the data structure, and these three edges would collapse together back into one edge. And that gets a little bit complicated as you have kind of nested insertions and you need to manage the data structure. But there are a bunch of algorithms we worked on to try and maintain that. But the basic idea is we're going to drop in these new green circles, and then we're going to take them away. And we're going to create a visual interface that lets people do that based on the statistics that we calculate. So once we have this kind of data structure, we're going to represent it in a very similar way to what we saw in the previous visualization. So we're going to take those nodes, represent them as squares or rectangles where the height corresponds to the number of patients or the number of event sequences that goes through that path. And the horizontal position from left to right encodes the sequence in which those events occurred. Then we can link those together to show basically the graph structure that we have in our data structure, and then add additional information to capture timing and color coding for outcome, and we have our final representation. All right. So what does this look like in practice if we're going to actually put this into an interactive system? So here is a video of our decision flow system. The user is going to author a visual query first. They're going to put in the first constraint, which is coronary bypass surgery, and then drop in heart failure as the outcome measure. And we're going to add a time gap. So we're going to say we want 1 year's worth of data before the coronary bypass. Then we want to label our patients as either being good or bad based on the occurrence of heart failure. So that's going to go out to the system, and we're going to get a picture like this. So the top shows that basic representation. It's very simple to start with because we just have our milestones, the start of the time window and the coronary bypass. On the right-hand side, we see a bunch of statistical information, number of patients, the average outcome, gender distribution, and all the different kinds of events that happen as those intermediate events. So even in this relatively small example, we have nearly 3,000 event types and about 500,000 individual point events that we're trying to look at and summarize for this set of patients. And what we can see from the right is that there's kind of a long tail. There's a lot of events that happen, many of them not too frequently. And on the bottom in the middle, we have a scatter plot, which allows us to look at the events that happen more often than just once or twice. We have kind of a threshold where we filter some things out if they're occur just once, for example. But then what we do is we plot each event type with a circle, and the two-dimensional space is defined by the positive support and the negative support. So the proportion of patients with a good outcome that have an event, and the proportion of patients with a bad outcome that have an event. And what we can see is the things that hover around the middle, that yellow line, are things that are equally likely to appear in both good patients with good outcomes and patients with bad outcomes. And so statistically, they're not really associated with outcome. But we can see that there are some red ones here, especially towards the top left, which are much more common in the bad outcome patients. And there are also some that deviate a little bit towards the green side, but not too many. What we notice first is that there's this big red circle on the top, all the way on the left side, which corresponds to one particular event. And if we look at it, it's actually heart failure. So that's interesting. That's our outcome measure. So what we can do is go ahead and right-click on that and filter it out. Now, the reason we want to filter it out is because we've queried for a bunch of patients. We've gotten a year's worth of data up until their coronary bypass. and then we've labeled them as having good outcome or bad outcome, depending on whether they get whether they have a heart failure diagnosis after their coronary bypass. Well, it turns out the most predictive thing about whether you get heart failure after your coronary bypass is whether you had it before your coronary bypass. So it's not surprising, but it's something that you would kind of overlook. You might forget to exclude those kinds of patients, and it jumps out at you right away from the visualization. So now we've narrowed down, we've excluded about 400 patients from our list very quickly, and we can continue our analysis. Now the next thing we see is that there's another red event here with a solid outline, which means it has a higher statistical confidence, and it's loop diuretics, a drug. And we can see that it's actually present in only about a quarter of the patients, but those patients had a worse outcome. We just adjusted the color scale to emphasize the differences a little bit more. And we can then further our analysis by looking at the events, the intermediate events that happen kind of before the loop diuretics and the intermediate events that happen after the diuretics, and use the visualization to compare across this very high-dimensional feature space. And we can see that there's this one particular lab test which was very strongly correlated with positive outcomes, and even stronger when it happens early in the patient progression. So we can add that lab event to our visualization by dropping it in as a new milestone. We turn that one edge into 3 pieces, and we get a visualization like you see here. Now, we can do the same thing and add that same lab test after the loop diuretics to start to compare, again, the details of what is in common between the patients who had that lab test before and people who had that lab test afterwards. And we see that most patients who had it before also had it afterwards. But there's a small group, which I'm pointing at now, which had the lab test before but not afterwards. And you can see that their benefits and outcomes kind of stuck around. In this case, only 17% of that selected group got heart failure after the coronary bypass, whereas the overall patient group had 44% outcome rate, and kind of the unselected group, the ones who didn't have that lab test, who followed that same path, actually had 50% incidence of heart failure. So again, we're not doing anything about causality, we're just looking at kind of correlations. So we're generating hypotheses that you then want to go out and do additional analyses to try and find. But we've created an effective tool that allows you, through prioritization of the many dimensions and the user interaction, to navigate data sets that have many thousands of event types without pre-selecting what you might be interested in. So that lets you scale quite well, and user evaluations have shown us that it's actually quite effective in letting people answer questions quickly and accurately. But it kind of doesn't end the story, right? It actually only introduces a few more challenges, which leads to some of the things that I'm exploring actively at the moment. And that leads, it's basically tied to the success of some of these earlier methods, which now allow us to quickly and interactively slice and dice the data really fast to narrow down to specific subsets of information we want, or to tease through tens of thousands of dimensions and anchor on to the 1 or 2 that we think are most statistically interesting. Well, both of those present kind of their own challenges. So if we're easily able to select a subgroup of patients out of a bigger pool using only a couple of different dimensions as filters, well, it may be that out of those other 9,999 dimensions that we're kind of leaving out of this filtering process, there are actually a lot of interaction effects because our dimensions are not going to be independent, right? There is a lot of association between the different features we have within a medical data set, for example. So the problem with visualization, in some sense, is its success, is that it makes it easy to apply these filters. It makes it also very easy to ignore all of those dimensions that are missing within the visualization. So that's one challenge. The other challenge is we're also using statistics to try and prioritize and rank, if you will, the types of features that we think the user, the analyst, might be most interested in. And to do that, we're going to do things like correlation. We might use even p-values to flag the way we're drawing things to help people filter from things that are unlikely to be meaningful to things that we think might be more likely to be meaningful. But more likely to be meaningful doesn't mean meaningful. It may be that we're essentially overfitting our visualization to the data set that we have across these many dimensions. So to address those challenges, I'll kind of try and shift towards a conclusion of my talk here by focusing on some of the things that we're working on actively at the moment. And the first of these is something called inline replication, which my team is looking at, which is the idea that rather than represent the whole set of patients who have a particular event or a dimension as one circle in that scatter plot that you saw previously, which we can flag as being statistically significant by drawing a thick border. Instead, can we borrow ideas from cross-validation in the machine learning community to essentially subdivide our data set into multiple folds or pieces, then apply our statistical tests multiple times to each of those and see which ones repeat? Do we get a statistically significant score across multiple of those folds? If so, then maybe we have more confidence that we're seeing something real rather than just being at the margins and discovering something based on noise. That also gives us the opportunity to partition the data into those folds across different aspects of our data set so that we can test to see, for example, is it repeatable across different medical institutions if we can subdivide into folds that correspond to our different data sources. And then we can kind of embed that into the visualization pipeline so it's an inherent part of what we're presenting to the user. And we have a very simple mock-up proof of concept of that idea and some results you see here. If you look at the bubble on the left, there's this tiny gray little dot inside the picture. That's actually the spread of this value across multiple folds. And it's very tight, it's very narrow, so it gives us some high confidence. Whereas in the picture on the right, you see there's a larger gray region with the dotted lines. Actually, that's the same thing we're drawing on the left. It's just so small you don't see the dotted lines. On the right, what we're capturing is the spread of those statistical measures, the positive and negative support, for example, across multiple folds, and we're drawing a convex region around those observations. And it gives us a sense that there's more spread within what we're observing, and so therefore we have less confidence in what the visualization is trying to show us. So the other piece of emerging work that I'm working on is something that I've tentatively called baseline exploration, with the idea that as we're applying filters and excluding groups of patients and including different groups of patients, what we'd like to do is actually track the history of our cohorts and then quantify over time the underlying changes to the distributions across all of those dimensions that we have, well beyond the ones that we're actually visualizing, but get a summary statistic across the tens of thousands of dimensions we have, and then try and visualize those confounding changes and allow people to compare cohorts and understand what's different beyond just the things that I've actually filtered. What other confounding effects have I kind of created? And then exploring ideas to actually compensate for those, perhaps by reweighting or adjusting our filters. All right, so to wrap up, I talked about outflow, where we started with selection and aggregation as a way to try and get around the high dimensional problem. We then moved to decision flow, where I talked about prioritizing the different event types and using user interaction to allow us to add complexity interactively into the visualization based on what the underlying analysis results told us was perhaps relevant to our outcome measure. And then I talked about a couple of our emerging lines of research, including the inline replication work and baseline exploration, to try and overcome some of the challenges that we have now that it's easy to navigate through this high-dimensional data. How can we make sure that that data is reliable and that we're not just overfitting ourselves to a bunch of noise? So I'll conclude by saying that I think this line of direction is really important. There's a lot of temporal data in a range of fields, as I mentioned before, and particularly in healthcare, where we are desperately trying to figure out how to improve outcomes and use our different interventions more effectively. I think there's great opportunity both for analytics, visualization, data science as a whole to try and make inroads in developing tools that help researchers understand the different paths that exist, and in the end, help clinicians choose the best path with their patients to obtain the best outcomes. So with that, I'll conclude, and I'm happy to answer any questions.
Okay, thank you, David, for presenting today. Really interesting talk. Again, if anyone has questions, if you can either type them, actually we prefer that you type them into the chat box, but if for some reason you don't have a keyboard around, feel free to just speak up. Anyone have questions? Sid, you want to?
Hi, David, this is Sid.
Let me.
Hi, David, this is Sid from Lindsay. I'm with the visualization group here. Very interesting work and very thoughtful visualizations overall. I was curious, you've looked at aggregates and counts of patients in different events, but have you looked at the effect of differences in duration between different events. So if a certain medication was applied at a particular time and at a later time, a different gap between applications of two medications for different patients. So that's the first part of the question. The second is how would you, so that creates a more complicated analysis, and how would you visually encode that? Thank you.
Right, so I have not actually. It turns out that in working with a lot of the practitioners, often the duration between events it seems to be overlooked, actually. And I agree. I think it seems like it'd be a valuable thing. I think people tend to focus more on the order in which things happen. So I haven't drilled down as deeply in kind of more powerful tools for doing the time gap analysis, rather than just showing essentially the average duration. But I think a lot could be done. I agree. It would introduce kind of a whole other level of complexity to the visual design. But I think there are a lot of things you could do. I can imagine showing, building in ways to show not just the average, which we show, but actually the distribution of time gaps within the set of sequences that go through one edge in those visualizations. And then you can imagine allowing people to draw cut points, perhaps, where they might want to add a breakpoint to split a path into two directions based on people who are below a particular gap or above a particular gap. And that would allow you to kind of break apart people who move quickly versus people who move slowly. So that's kind of, just quickly thinking about it, that seems like one possible way you might be able to add that in. I think for problem sets where the domain practitioners are really interested in that timing gap analysis, I think it's a really interesting problem. I think there's a lot of fun work that could be done there.
Okay, thank you.
Okay, we have another question here, and I'm going to read this to you, David. It came in as a text. What programming tools or languages are you currently using for this analysis and visualization?
Sure. So the tool chain has evolved over even just a couple years of kind of time span that you've seen in this presentation. But that just reflects how quickly technologies are changing. My current tool set is basically building web-based user interfaces. So I'm putting everything in terms of visualization is being rendered with D3, which is maybe the de facto standard, if you will, for visualization these days. There are a lot of other toolkits out there, but I think D3 is the one with the biggest community around it now. As far as for the back-end analytics, I am working almost exclusively in Python these days, taking advantage of a lot of the machine learning and other statistical analysis routines. And then just kind of gluing those together, I use a simple web framework called CherryPy, which plugs into Python, but is a very lightweight web framework that makes it kind of very simple to connect to a website, but doesn't give you all the heavy machinery that comes with a lot of the larger toolkits.
Okay. Any more questions for David before we wrap it up? I'll give you, what, 5 seconds, people. 1, 2, 3. All right, I guess that's it for now then. So once again, David, I want to thank you for presenting today. We really appreciate it. We also appreciate the time of our attendees who spend their lunch hours with us. For all of you in the audience, remember DataBytes is a monthly lunchtime webinar series. Our next session is Tuesday, October 6th. Once again, it'll be at noon Eastern Time. And we're going to feature another one of our NCDS Data Fellows, Eric Stahl, who is with UNC Charlotte, and he will highlight his work on machine oblivious graph analysis. We hope you can join us then and look for more information from us coming shortly. David, thank you once again. Thanks, everybody. Have a great rest of the day.
Great. Thank you.
Thank you.